Hello everybody. With this post-lecture video, I would like to complete what we were doing yesterday at our lecture. Remember that yesterday we were talking about how we can now use BJT amplifiers in more complex architectures, making amplifiers seem even more powerful, and so on and so forth. And we said that the four key parameters that we had discussed about the week before during our 9th lecture are the input impedance of the circuit, of the amplifier circuit, the output impedance, the voltage amplification, that we called AV infinite, if you remember, and the current amplification that we called AI0 at no load. So we demonstrated yesterday in our chat that simply by using these four parameters, we can then build cascade amplifying circuits, and we are able then to predict, if you like, which will be in the end the overall amplification of the cascaded system. Related to that, toward the end of the lecture, if you remember, I was about to show you some demonstration maybe of, first of all, how the amplifiers we looked at not yesterday, but the week before, when we did the CE, the common emitter amplifiers. So I wanted to go through some of the calculations of these four parameters with you, but also then show you practically a demonstration of how indeed both the DC analysis of these circuits and the AC analysis of these circuits done, on paper, let's say, actually reflects what happens in reality, obviously. and I was going to do that. Well, yesterday I only just started this part, and if you remember, I started doing that using LTspice, so a simulation tool. I told you that I was planning to actually come in the lecture with equipment and show you, a real demonstration of amplifiers, but that was not possible, unfortunately. So I decided to do it with a simulation tool, which is fine as well. Actually, it's even more versatile, to be honest, and probably will be more useful for you if I tell you more about also this simulation tool. This was the plan. So I would like with this video to effectively show you these applications of amplifiers, eventually cascading amplifiers, and then compare what we would expect based on theory compared to what the simulation results provide us. So I will start first this video with showing you LTspice very briefly, just so you know where to find it, and then I will go through the examples that I only just briefly started yesterday, and I would like to go through all of them so that you have a clearer idea of how LTspice works and so on. So thank you for watching, and I'll see you next time. Bye. Okay. So first of all, let me spend a few words on LTspice. Oh, sorry, you don't. Yeah. Let me spend a few words on LTspice. First of all, where can you find LTspice? So, just a moment. So you can find LTspice. LTspice is a product that is a software that is offered free of charge by this company, Analog Devices. And if you type on any search engine LTspice, you will end up on this web page here. And you can download it, install it, and the nice thing about LTspice is that it comes ready with all the a very large number of ready models for different components, like many NPN transistors, BJT transistor, PNP, operation amplifiers, and just so you know, many companies actually provide this type of simulation tools. It's a way for them to, I understand, promote their own devices. Analog Devices is one of the semiconductor manufacturers that produce many components that we use in the lab, probably. So that's why this is provided free of charge, but you can find many more. So there is another one I came across which was is called the LCspice. So similar story there. Again, you can find lots of models and so on and so forth. But I found LTspice quite nice and easy to use, so that's why I'm suggesting this. By all means, feel free to use any one you like. So once you download it and install it, it takes 5 minutes to install, and you end up with this interface, and straight away you can create a new schematic. You can on this toolbar, you can pick up the instruments you want to use. So here are more the components, so ground, labels, resistors, and so on and so forth. So for example, if I wanted to use a BJT, I would pick up first a general BJT, this one from this list. As you can see, there are also many folders here that you can use. I'm not an expert in using LTspice myself, so what I generally do, I pick up a general NPN BJT transistor, for example, and if this is a very general NPN transistor. If I wanted a specific model, you can click on this and say pick new transistor. And it comes up with a list of several BJT transistors available with their characteristics here. So if you knew you wanted a specific model, you can pick it up. So for example, I remember that in my lab I have the BC337. So for example, I could try, maybe I need to order this like that. There you go, BC337. So I could say, okay, so this is now the BC337, and you can now start building the circuit, whichever circuit you wanted to build. I mean, here you can use many other things. So obviously, diodes. Again, you can find a specific diode if you want, if you know the model, and so on and so forth. And digital gates. So to pick up just for the sources, there is in this list here, the main list, there is here this current source. This is very general current source, can do everything, DC, AC, pulse. So you pick that one, and then once you put it on the schematic, you can decide what you can define what it has to do. For example, for voltage, if I put here my voltage generator, I can then click on it. This is the brief dialog panel. Here you could put just the DC value if you wanted, but if you go on advanced, here you can really define a lot of stuff. So you could, for example, if you put a value here, this would be then an AC would become an AC voltage source. If you put a value here, it would become also a DC voltage source, and so on and so forth. And here you can done a lot of other functions, as you can see. So this is in general how really few words about LTspice, and just to show you how then once you have a circuit, just to show you how then it works, let me bring up the little simulation, the little schematics that I've made on something we should know, which is the IV characteristics of the BJT transistor. So I've made two schematics. One is for the input characteristic and one is for the output. Let me start probably from the output, which is the one that we probably know better, which is this one here. Let me make it a bit smaller. So again, I'm using the BC337, which is the one I have in my lab, and I know it very well. And then I have on IB, I want to do the output characteristic of the BJT transistor. So if you remember, I need IC on the vertical axis, on the ordinate, on the abscissa, I need VCE. So that's why I have here my generator VCE. And then I need to, every time I do a sweep in VCE, I need to have fixed IB. So that's why I put this comment here, just to explain you what this command down here does. So this is telling the simulation that I will run in a moment to do a DC sweep of VCE from 0 to 5 with a step 0.001, and each time the sweep finishes, change the value of IB from 0 to 0.001 amps with a step of 0.0001 amps. So IB basically is changing from 0 to 1 milliamp with a step of 100 microamp. So this will generate the IV characteristic, the output IV characteristic of the BJT transistor, as we've seen it in the lab. And that's effectively what I just explained to you. So use VCE as an independent primary variable, is the variable we sweep on, the primary variable, which is swept from 0 to 5. And then each time for a fixed value of IB, which is instead the independent secondary variable, which is instead swept from, in this case, 0 to 0.001 amps. And in the plot, the abscissa will be always the primary independent variable, which is VC. Normally in the ordinate we choose what to plot. I think in this case I've already the plot is pre-filled by myself because I did it previously. But just to let you know how this comes about, Spice is a command line software. So this is effectively a command that the software can interpret to do something, as I explained to you. But LTspice has a nice little tool here. If you go to simulate and add the simulation command, you can see that I've selected here the DC sweep tab, and I've selected the sweep I just described to you is actually represented by those entries that I put here. So my first source is VCE, as I mentioned already. Is VCE, and it's a linear sweep, goes from 0 to 5 with an increment of 1 millivolt. So I'm doing a very fine sweep on VCE. So whatever, if you change something here, you can see here already that there is a command that is ready to be pasted on the schematic. So if I change here, for example, this to 6, you will see automatically the command has been changed. So the part related to VCE has now acquired there the change that I made. So let me put this back to 5 just in case. And then the second source, the secondary variable, is the IB value, which you need to put the right name here, the name that I've used also in the label. and it goes from 0 to 0.001 with this step, and this, once you fill it in, it appears here as this second entry. Once you click OK, the command is pasted and replaces eventually the previous command that was there. Now, obviously, I didn't do any change, so the command is there. So since I've set up now the simulation is ready to run. So if I click on this one, this will perform the simulation as I've set it up, and will also plot it. Now the plot was already set up, I think, so it will appear. That's it. Let me just show this like that, which makes more sense. And here we go. We see here we have IC, because I'm plotting IC, as you can see, up here. Sorry, let me remove my face. That's it. So you can see I'm plotting IC versus, and this we said is the primary variable, which is VCE. So this is the output characteristic. Each line, each different color, corresponds to a different value of IB according to the sweep I defined for IB. So according to the parameters I've chosen, this corresponds to IB equals 0, this 100 microamps, 200, 300, 400, 500, 600, 700, 800, 900, 1 milliamp. Okay, so as you can see, we can already get a feeling of what is the beta of this BJT I'm using for 100 microamp IB. I'm getting an IC that is of the order of, maybe 30, 40 milliamps. So it's a quite large beta of the order of maybe 300 or 400 or something like that. So quite large. And indeed, I know that this BJT transistor has a quite large. I don't recall it to be so large, to be honest with you, around 250 maybe, if I remember well the datasheet. But anyway, always remember that this is a simulation tool. So as any simulation tool, there are obviously some limitations anyway. And so this is the output characteristic. Let me show you. Remember, once you are happy with the plots you do and the simulation, the schematics you've made, remember you see the plot and the schematics appear in these tabs. Remember to save them, so you can click on each one of them and save it. Click and save it so that everything is saved. Normally, LTspice creates a folder in your documents folder. So if you have not saved the schematic elsewhere, that's where in that LTspice folder, in your documents folder, is where you will find normally your stuff. Otherwise, and that's what I generally do, I save them elsewhere. So before you save it, click Save As and decide where you save it. Automatically, it will keep saving it obviously there. Now let me show you the other characteristic of the transistor, so you get to know a bit better also LTspice. So the input characteristic now. So the input characteristic of the BJT transistor is obtained by using this type of circuit. So again, we have VCE applied to the collector, and but this time, instead of a constant current generator on the base, we have a voltage generator that is applying a certain VBE to the base and the emitter. This time, VBE is the independent primary variable. So what we want to do to create the input characteristic is plot IC versus VBE. Eventually, we could use VCE as a secondary parameter, but we will see this doesn't play really a role. And we could also plot, together with IC, we could plot also IB to have both, if you remember. I think in class we showed both. And that's what this this simulation, as I've set it up, does. So as you can see here, the command is do a DC sweep of VB as a primary variable from 0 to 1 with a step of 0.001 volts, and the VC, the secondary variable, is swept from 1 to 5 with a step of 1. So I will now run it. Let me show it the other way around. Let me remove my window. So in green is plotted. So remember, in the abscissa we have VBE. In the ordinate, we are plotting current, both IC in green and IB in blue. So what we see here is that I've chosen for the moment the logarithmic scale here, just to show you in full the behavior of IC and IB. As you can see, both IC and IB, if you remember, we are sweeping also VC. VC is our secondary parameter, which goes from 1 to 5 at step of 1. So here you can see that there are indeed five curves, and these are for the 5 different values of VC. For example, here the bottom one will be for VC equal 1, 2, 3, 4, and 5. What we should note here is that really for the values of as when the BE junction starts to conduct some current, which is basically, you can see, above 0.3 volts, effectively the value of VC is not so important. All the curves here are one over the other, both for IB, for IC, and for IB. Now there is clearly this part that is exponential. We've discussed this in class, if you remember, and then this curved region is where the junction's characteristic starts to become linear because of, if you remember, because of the non-ideal effects that are at play in the junction. We can one last thing to note here is the fact that, and this is the key element of the BJT transistor, is that for a given value of VB, we see that IC and IB, eventually the ratio between these two values is always the same, and this is what makes beta constant. Okay, this is really the key element of the BJT operation. We could see this plot also in linear mode, which would probably make more sense. And so obviously we see only IC because IB is much smaller, is hundreds times smaller than IC. But you can see here clearly the behavior I just told you. You can see this is just the linear behavior. The exponential, we can't see it on linear scale because it's buried down here. We could look also at IB. I need to remove this trace here and rescale, auto arrange. There you go. So this is IB. So this is IB VB. So this really is the characteristic, IV characteristic of the B junction now. And we can see that this is really the linear part, if you like, of the IV characteristic, because this is now a non-ideal junction, and as we've seen in class, at a certain point becomes linear because of series resistance effects. So this is a good way, I think, to introduce you LTspice, and the nice things you can do with this, from something as simple as checking out how the BJT operates to, as we will see in a moment, looking at amplifiers and so on and so forth. So let me close this and let's go back to our amplifiers now. So So the plan is this. I would like to do the full calculations of one of the amplifiers we have gone through 2 weeks ago, and also maybe 3 weeks ago when we discussed the DC biasing of CE amplifiers, and the week next we discussed the AC analysis of the CE amplifiers. And so I would like to see this all together for one example, and so here it is, the CE3 configuration, the voltage divider amplifier with RE bypassed. This is the one we've discussed in the past weeks. One of the 3 configurations we've discussed, and there was actually an example we've gone through. I think this was in week 8. When we discussed the DC biasing of these configurations, and the example was this one here. So the data was, we have VCC 15 volts, VB on is 0.7, and the question was find R1, R2, RC, and RE in such a way that IC was 2 milliamps, VCE is effectively 7.5 volts, half of the VCC. VE was a quarter of 15 volts, so 3.75, and making sure that I1 and I2 is much bigger than IB. So effectively, this current and these currents are much bigger than this. And effectively, if you remember, we said we could, in this, I think in this specific case, I solved it saying, okay, let's set I1 and I2 equal to IC, since IC is anyway much bigger than IB. But on top of that, what I would like to do now is also to use what we learned from the AC analysis of this configuration, calculate effectively what would be Z in, Z output, AV infinite, and AI0 for this configuration, assuming that HFE is 100 and HI is 1 kilo. So here are the calculations. So I remember from what we did from the DC biasing in chapter 4, common emitter operation, we solved the DC biasing of this configuration, and we found out that we needed R1 equal to 5.27 kilo ohm, 2.23 kilo ohm, and 1.88 for RE and RC. So using these values and using the results that we've learned from the AC analysis of the CE3 voltage divider configuration, we know that, for example, the input impedance is given by this formula. So if we put everything in, the values that arise from the DC analysis and also HIE, we assume is 1 kilo ohm, we get that roughly input impedance of this circuit is roughly 610 ohm. Also, IAV infinite, remember, AV infinite is the voltage amplification calculated when we are assuming that the load is infinite. So effectively that whatever we are touching at this point is effectively an infinite resistance, or it's an open circuit as it is there. So in this case, AV infinite is given by this quantity. So assuming HFE is 100, obviously this depends on the BJT in the end, but let's assume it's 100. HIE is 1 kilo ohm. RC is set to 1.88 kilo ohm, and so we get roughly minus 188. Which is quite large, obviously. And similarly, AI0. AI0 is the current amplification that is defined as the current amplification when the load attached to the circuit is effectively 0. So we are effectively delivering the maximum current we can. to a load that has no resistance. And so this is obviously the maximum current that the system can deliver, and so this is the maximum amplification eventually that the system can always eventually present. And we've demonstrated that this amplification should be given by this formula here. And if you do the calculations, this should give you minus 61 roughly. And finally, the output impedance for this configuration would be RC, so 188 kilo. That's all good. So I will show you in a moment. We've also discussed, I think, this example already yesterday in class anyway, but I will do it again anyway, just so for completeness. So I've run this circuit with LTspice, and what I got, and I will show you in a moment how to do everything. I got for the input impedance indeed 700 ohm, which is quite close to the 610 I had forecasted previously. For the voltage amplification, minus 140, which it's a bit off, but not too much, considering that obviously I'm assuming for HFE a value of 100 without knowing, this depends. These values here, HFE and HIE, depend on the BJT. So obviously this factor is heavily affected by the fact that I don't know which BJT I'm using. So in this case, I'm using a specific BJT, which I think is the BC337 probably. We will see, I don't remember. So I'm happy anyway, they are the same order of magnitude, let's say. AI0 minus 53, and the output impedance is indeed roughly 1.88. So you can see that the biggest discrepancy between model and the values I calculated are where the final result are where the quantity heavily depends on the hybrid model parameters that obviously in this case because they depend specifically on the transistor that I'm using, and obviously in this case, in this example, I didn't specify which transistor I was using. I just assumed that HFE was 100 and HIE 1 kilo. So let me show you the circuit. I will give you later on these circuits as well, so you have it. RE bypassed. So this is the circuit. So we have our input signal, which is an AC signal with 1 millivolt amplitude. This is the CE3 voltage divider configuration with RE bypassed, as we did it in class. And here is our output initially on a very large load, which in this case simulates effectively an open circuit. It's a very large resistance. In this case, I don't know, is 1 megohm, which for us is equivalent to an open circuit, infinite resistance effectively. Oh, if you notice here, I've added a resistance that simulates the eventual series resistance of this generator. I've done it like that to be able to show you a trick on how to use this to estimate the input impedance of the circuit. Same story for the load. I've already probably shown this to you yesterday. We can use the load to actually as a trick to find to estimate the output impedance of the circuit. Anyway, let's first check this amplifier and see how it works first of all in DC. You can see here there are already two commands. One is for the AC operation, and one is for the operating point. So let me. So this was the this is the command to find the operating point. I will comment this command. We don't need it now. We'll do this later. So if I run now the simulation, this will provide a table with all the values of the calculated through the DC operating point of this circuit. So there you go. So obviously I stress this is only DC, okay? There are a couple of things to check based on our design. So let me go back to the design we had. So our design rules were, for example, IC must be 2 milliamps. Let's see if that's true. IC is indeed, it's 1.91 milliamps, which is quite good, very close. Then the other thing was that VC had to be VCC over 2, which is 7.5 volts. Let's have a look. VCE, so you need to do VC, which is 11.4, let's say, minus VE, which is 3.6. And let's see. Let me check. 11.4 minus 3.6 is 7.8, which is also quite good. Very close to 7.5. The other thing to check is VE. There should be, according to the design, VCC over 4, which is 3.75. And indeed, the VE is 3.763, sorry, 3.6, which is also very good, very close to the value that we had set. And then we can check that according to the design, I1 and I2 had to be around 2 milliamps. So we can check that indeed these two are more or less the same, I1 and I2. So I will check IR1. IR1 is this one. You can see that it's 2 milliamps and is very similar to IR2, which is also 2 milliamps. You can see that they are nearly identical. And the reason is that because IB is very small, obviously. Where is IB? Is here. You can see that IB is 1.9 10 to the minus 5. 1.9 10 to the minus 5. So it's 19 microamps. 2 microamps, let's say. Sorry, 20 microamps. And so from this we can realize that the transistor, this is the generic BJT I'm using from LTspice, it has a beta factor. You see that IC is 2 milliamps, this is 20 microamps, so the beta factor is, the DC current amplification is 100, effectively. Okay, and what else? We can check that VBE is roughly 0.7. VBE, for example, in our calculations, sorry, in our calculations we had set VBE on to be 0.7. So let's check how much is it for this transistor. VBE is 4.43, 3.64. How much is it? 4.43 minus 3.64, 0.79. So it's very close, obviously, to 0.7. And so I think this is, the checking the DC operating point is very important in this way. So it shows you really what we do with our formulas and so on and so forth. Really, it reflects what will happen then in reality. So that's a very good check here. And let's go now to the AC analysis. So let me comment this one and So again, remember that the DC simulation or the IC simulation is the command that has to be pasted here can be defined by these tabs. So for the DC simulation operating point, you do it here. You just say, you don't need all this stuff. Always make sure you clear the command, and then once you go to the tab, this will automatically just add the .op operating point as I did there. And so for the AC analysis now, this is the command, and so we analyze. Note that everywhere I'm using for the capacitors values of 100 microfarad. I will show you in a moment what's their effect. So if you simulate this now, you can do it like that. So here, because the simulation is sweeping in frequency, so it does it provides us the frequency response of this circuit in AC. From the settings I've given, it is I'm doing effectively a baud diagram. So the frequency is divided in. I'm taking 10 points per decade, from 100 Hz to 1 megahertz. That's on the abscissa. And now I'll decide what to plot here. So first thing to check, since we have the series resistance is 0, and that's how we did always in all our AC analysis stuff, we always assume that there was no series resistance from the generator, so I'll keep that to 0, and we will keep the load to be very large for now to simulate an infinite output resistance, an infinite load, so that now we could calculate with the simulation I've just run the voltage amplification. So I calculate the voltage amplification by plotting V output over V in AC. If I plot this, let me put the plot in just logarithmic probably. So we can see that the amplification indeed is around 140, as I had put it here already. See, this is minus 140. And sorry. So let's now check the current amplification. To check the current amplification, we said AI0 is the maximum current amplification that is obtained when the load is actually 0. So I need to change the load. I need to go back to the schematic, set this to 0, and run again the simulation. And now I want to plot the output current divided by the input current. So I need to find on the output, I have, let me see, what can I take? I could take ICO, so the current through CO, divided by the current through this capacitor here. So in AC, this will give me the current amplification. So if I do this, we get that the current amplification is roughly 53. Oh, I forgot to mention that, as you can see, the phase, at least at, is very close to minus 180 degrees. And so this means that there is a pi phase difference between one quantity and the other. In this case, the output current and the input current was the same. I forgot to stress it for the voltage in input and in output. And so this means that this explains for the minus in the amplification. So now let us use some tricks to calculate, to estimate maybe from the LTspice model, which is the input impedance of the model, which is the output impedance of the model. Let's do the output impedance first. The trick I use is I look at the voltage amplification. Okay, so what I will plot here will be the voltage amplification But the idea is this. We know that AV infinite, when the load, the output load, let's first try to calculate, to estimate the output impedance of the circuit. We've seen already that AV infinite is minus 140. This happens when the load is infinite. Now, if we change the load to a value that matches exactly whichever is the output impedance Z0, ZO of the amplifier, ZO together with the load will create a voltage divider. And if RL is equal to ZO, this will halve the voltage in output, the voltage divider. So this means that I should be able to see that the total amplification of the circuit will drop to half this maximum value here. That's the trick I use. My starting point is the value I found from my calculations, which is 1.88 kilo ohm. And so I will set that here on R load. So 1.88K. Let's see what we get. So 69, very close to 70. So indeed, this is confirms that the output impedance of this circuit is exactly 1.88 kilo. So let us now have a look at the input impedance. Let me put this back to infinite effectively, something close to something very big anyway. So I'll put it to 1 megohm. So I want to look now at the input impedance, and I will play now with the series resistance of the generator. So similar story now, similar trick. So we have a hint that the input impedance of my CE3 voltage divider amplifier is around 610 ohm. What I will do, I will set the series resistance of the generator to 610 ohm. I should verify that the voltage amplification of the entire circuit should go to half when I match the series resistance of the generator to the input impedance of the amplifier. Let's see. Let me start with 610. So we should be able to, the AV infinite, remember, was 140. So we need to be able to get 70 again. So let's see what we get now with this one. So with 610, I'm getting a bit above, I'm around 75. So I will drop, I need to increase this a little bit. So let me go at 700. There you go, 70. So the input impedance, according to this model, is around 700. Okay, so I think these are especially those things I've shown you about how to estimate the input and output impedance from the simulation are some nice tricks that you can use for the purpose. And so at this point, so we verified that our calculations are relatively close, isn't it, to what the simulation, real life, let's say, would have given us. So, at this point, the question is, fantastic. I know how this amplifier behaves. What would happen if we now say, let us cascade 3 of these amplifiers using C coupling? So I want to do this now. You can see that each one of these things is one of our amplifier we dealt with above. So the question is, which would be the total amplification, for example, in voltage of this thing. We could do the same for the current amplification, but let's just do one. That's the important thing is to learn how to do these things. Doesn't matter what it is. So let's do the voltage amplification. Based on what we said yesterday, the voltage amplification, the total voltage amplification of a system like this is given by this formula. Oh, sorry. Yeah, much better. So is given by this formula, which we, if we specialize to this situation here, becomes this first term, which relates to the first stage. So the input of the second amplifier divided by the output impedance of the first plus Z input of the second time AV infinite 1 time this term relates to the second stage, and this term relates to the third stage. The third stage, because it's the last stage, is a bit special because obviously it doesn't see the input impedance of another stage. Sorry, you won't be able to see this. The third stage is special, I said, because it won't see the input impedance of another stage, but eventually will see the load resistor, and that's why it takes this different form. And so by calculating just this quantity, I'm calculating the amplification of the first stage when it's connected into the cascade. So effectively V out 1 over V in 1 in the cascade, which is different, as you can see, from just this amplification because it's in the cascade. All this quantity here calculated, multiplied together, will give me the voltage amplification of the cascade of the first two elements, and then the whole thing will give me the total amplification VO3 over V. So to do this calculation, obviously we need AV infinite, we need Z in, Z output. So just to make sure that our calculations are based on the right numbers, and since in our simulation we will use the same transistor we used previously to do the simulation of the CE3 amplifier by itself, and we got these values here. So to calculate theoretically what we expect, I will use these values that we obtained from the model, just to be more relevant for the simulation as well. Okay, so we will use, as I say here, we will use for Z input 700 ohm, Z output 1.88, and so this quantity here, which appears obviously identical here, and no, only on these two, is 0.271 if you do the calculation. For AV infinite, we will use minus 140 as we found from the simulation. So what do we expect? We expect, based on the formula we wrote above, that at the first stage, the amplification V out 1 over V in 1 should be minus 37.9. At the second stage should be plus 1436. At the third stage, if you consider RL infinite, this should be this amplification, 1436 times AV infinite, which is this, so minus 201,000. I did this also with LTspice, and I got, as you can see, numbers that are exactly spot on with, those that we were expecting. Okay, and let me just show you. Just a moment. Let me just show you this simulation here, which is unbypassed cascade. So as you can see, this is the cascade of these three that we just discussed. Three CE3 voltage divider with unbypassed amplifiers in Cascade. The RL is infinite. Again, I'm using my AC voltage generator here. RS is 0, obviously. I'm not interested anymore now in using it. And so I've set it up to do the AC simulation here. Here we go. I've had already set up the three outputs. So the blue curve, the one down here, represents the amplification at the first stage in the cascade. So it's V taken at this point divided by the input, the voltage input. And you can see that this is around, so here is 10, 20, 30, it's around 40, indeed. Our theoretical calculations were telling us around 38, so fantastic agreement. And the red curve is the amplification at the second stage, and is around, I need to zoom in to show you, but this is around 1,300, 1,400. So very close to what we were expecting. And finally, the total amplification is around 200,000. Okay. Okay. So I think this was a very good exercise to first of all demonstrate you that everything you've learned obviously corresponds to what will happen in reality, and also it was a good to show you also how to use these nice simulations tools that allow you to get a more in-depth understanding of what you're doing. In my notes that I will give to you anyway, I've also done a second let's say practical exercise using this time the CE3 voltage divider, but with emitter resistance unbypassed. So you can see that this is what we call the RE unbypassed amplifier. Remember that this is something that, as we said, this specific type of amplifier, we said, will not be in the exam this year. It's enough the three configurations we've done that were all bypassed, at least C2 and C3 were bypassed, because they simplify obviously the analysis. But still, I've done this here. So here I remind you the fundamental results related to this amplifier. If you remember, the main point about this amplifier was that the AV infinite depends only on RC and RE, no amplifier parameters there. So that was the reason to even at least mention this type of amplifier to you. And so the exercise I'm doing here is to say modify the design the design according to the with the design parameters defined in the above problem, but in such a way that AV infinite is -10. So this means we need to set RC and RE in such a way that the ratio is 10. And so I do here first the DC analysis according to the same restrictions we had from the previous problem. So IC 2 milliamps, VCA equal to VCC over 2, and so on. So I mean, for fun, you can go through if you wanted to and have a look at what I've done. So I do the DC analysis as we know it. And so I find that, where is it? I find that it should be R1 equals 6.8 kilo ohm, R2 691, RE this one, and RC that one. And so based on the formulas of Z input, Z output, AV infinite, and AI0 for this specific amplifier configuration, I can predict maybe that I would expect an input impedance of 630, AV is in -10, AI0 is -1.7, and the output impedance is this one. And so again, I did the simulation with LTspice. There is no, I won't show it to you, just very briefly to show you that again, if you do the LTspice simulation, you realize that the input impedance is indeed 630, spot on. The AV infinite is indeed very close. AI0 also is really close, and the output impedance is also effectively that one. And also here I've done the same exercise of what happens now if you cascade this. And so again, same story. So we calculate the amplifications at each stage and at the end. I calculated again based on the model values Z in, Z output, and this factor here that is needed for the voltage amplification calculation. And so again, I predict that the amplification after the first stage will be minus 1.49. At the second stage will be plus 223, and then the third one will be, when RL is infinite, minus 21.4. And indeed, obviously, the model results also are extremely in very good agreement. So the only thing I forgot to stress actually also in the previous example is that, as you can see, after the first stage, there is a minus here that indicates a phase difference, but then that phase difference disappears here. You can see that the voltage amplification is positive now, and this is obviously because you are multiplying twice by something negative, and this effectively means you are adding another phase shift of pi, so pi plus pi is 2 pi, and so this effectively, it seems like no phase shift, no phase shift there. But obviously in reality there is a 2 pi phase shift, and so on and so forth. So that was everything I wanted to really show you. I believe, at least for some of you, this simulation tool may be useful in the future. But if I may be of help in any case, in any way, feel free to drop me an email, and if I can help, I will. Really, this closes this series of lectures and videos. So I hope you enjoyed this journey, and I can only wish you all the best. And I'll see you next time.